engineering at Gonzaga University in Spokane, Washington, and have been doing river restoration stuff as my research and professional development for quite a long time. Was a strong active member of River Restoration Northwest and the like. And then also, yeah, just been working and moving into over the last like 6 or 7 years. I've been doing work related to mimicking beaver dams or beaver dam analogs. And so that's sort of what I'm going to present on process-based restoration and using beaver dams in particular to attempt to trap sediment, maybe reduce nutrient loads downstreams for TMDLs and the like. And so going to sort of give an overview of what we've been working on here in Eastern Washington in the Pacific Northwest and yeah, happy to answer any questions along the way. So just to give some quick background, I'm sure people are familiar with beaver and particularly their dams and the benefits, but just to give an overview on that, just sort of sets the stage for why we're also trying to simulate their beaver dams and that because they do good things. But beaver essentially are the largest rodent in North America. They can weigh up to 90 pounds, anywhere from small to, they like to be in streams anywhere from small to medium size with low slopes so that the energy doesn't blow out their dams or at least too frequently. They also very much need wood in the stream system, riparian areas that contain wood because they eat wood, right? So that's their primary food source, particularly aspen, cottonwood, and willow. And then also use the wood. And this is a great video showing beaver eating some wood in someone's backyard as he was being relocated. But potentially they also use the wood for, of course, for potential construction materials to build their dams and lodges and the like. Right. So essentially they need water and wood, and then they end up creating their dams to provide their safe space. They do much better in water than on land and so they like the pond. They create the pond to build their lodge and then also store their wood supply for food cache in the winter, right, in the pond as well. And like, so they dam the landscape and that which creates impounded water. They have a natural instinct to stop the sound of running water. So it's cued if they hear water leaking through their dam, they must seal it, right? It is instinctual that they have to stop it. They've even done some things where they've buried inside of a beaver dam, they buried an audio box that's playing running water and the beaver will come and try to cover it up and so anyway, it's very instinctual to keep their dam sealed. They can construct their dams out of wood or other available debris. Ideally, they like to keep the prime wood for their food source, but they can use wood, mud, rocks. They'll even sometimes use anything else that they might find around to build their dams. Right. This is just a nice example of the world's largest beaver dam, found up in Alberta, Canada. It was found via Google Earth images in that, but it is essentially as long or longer than the Hoover Dam. So it's quite a large dam. And quite large pond behind it. But it's just a nice little interesting fact that there's a really large beaver dam out there doing its thing and that. So beaver dams and ponds, they ultimately build their dams in series. They create multiple dams to create safe transportation corridors to connect large ponds together. Their complexes will grow over time as they have to move further and further out to get the wood sources out in the valleys and so they will essentially grow over time and they like to do them in series to help protect their main dam. Well, now the benefits of their dams, really, it's like the dams that cause the positive ecosystem benefits. And so that's also why we're trying to simulate those dams with beaver dam analogs, but they increase water retention and base flow, right? They don't really hold the water and remove it from the system. They just really hold it longer and change that sort of spatial distribution and residence time of the water moving through the system. So create little storage areas over time. They also act as little detention ponds in a way, right, where it decreases the downstream peak flows through the storage that it provides in the system and reduces flooding downstream. Also expands habitat area and complexity out into the valleys. The more wet it gets and the wider that the ponds expand to, increasing wetland area, groundwater recharge. It helps water get back into the groundwater system, can also act to raise the groundwater table back up. And that to maybe feed vegetation in the floodplains. And then also, as seen in this lower right picture here, they do the dams and the wetland areas that are created by the beaver protect areas from wildfire, right? So there's a lot of research being done at looking at beaver dams in there, particularly with all the wildfires we have in the West, and that how the beaver dams in those areas help to improve the ecosystem and actually protect the ecosystem during wildfire as it comes through and the like. So So in addition, their beaver dams also improve water quality, create sediment retention. I like to think of beaver dams and now ultimately beaver dam analogs as speed bumps in the river to help slow down the flow, increase the ponding depth, and that to allow sediment to sort of fall out. So they increase water depth, reduce velocities, and dissipate energy. They also have an impact on temperature. So they can increase shade from the growth of additional vegetation by getting that groundwater table feeding the riparian zone again. Temperature stratification in the ponds, you get some cooler temperatures on the bottom. Also, they can force sort of some hyporheic exchange of the water down into the hyporheic zone, which can cool the water off too and allow for some decreased temperatures, which the fish and the habitat really appreciates. Right. They also can trap, in addition to the sediment, it can also allow for the settling out of nutrients, such as phosphorus and nitrogen and the like, and they trap organic matter. And then ultimately the local vegetation can uptake those nutrients in that rather than having them maybe transport downstream and create algae blooms and the like. So the question then becomes, why aren't beaver and their dams everywhere and in all river systems? And actually they were a whole lot more prevalent, right, way long ago before we eradicated a lot of the beaver but ultimately they need water and wood, right? So there needs to be in particular wood in the system as well as water. And if you look at this particular creek, which I'll come back to in a little while, but it's called Rattler Run Creek, and it is just south of Spokane, and it's out in the agricultural area known as the Palouse, which is the sort of one of the bread baskets of our country, right? It produces a huge amount of wheat, and that out in the Palouse, and a lot of ag and essentially sediment runoff. But a lot of the rivers and the creeks down there in the Palouse have been sort of straightened and ditched in order to be able to do the ag in the floodplains and the like around there. But as you see in this, it's pretty much a straightened channel that has some water in it, but for the most part, no wood, right? So there's no riparian vegetation, there's no wood there for the beaver to actually use, and so in the end, we look at streams like this and say, well, the beaver aren't there now, and they won't be there now because they don't really have in their dams because they don't have any wood to build their dams with or as a food source. But could we take a stream like this and replicate those beaver dams to maybe improve the ecosystem and the water levels and the like, and maybe come in and plant vegetation to bring that wood back and improve the ecosystem back to maybe eventually the beaver might come back in. And now it also depends upon context and watershed and what's around but can we simulate those beaver dams in order to do similar positive impacts on the ecosystem and that in this type of stream where we know beaver won't actually be at the moment and would take a while for them probably to come back, but can we learn from what they've done and try to replicate that? Right. So that takes us to what are beaver dam analogs, right? And so BDAs, as we like to refer to them, are a process-based river restoration technique that is looking at simulating beaver dams so that we can get all those similar benefits. The hope is that we can get the similar benefits to the natural beaver dams by simulating the dams ourselves, because the beaver can't be there to do it without the wood and the water. And so they are structures that are completely or partially built by humans that mimic many of the functions of natural beaver dams. They are built, now there can be a variety of ways that you can build these. You can have postless structures, or you can have, more commonly, the way that we build these are using wooden posts that are pounded into the stream perpendicular to flow, right, in order to be able to stop it. And then between those posts, we weave pine branches or willow branches or a variety of different types of branches, but you sort of weave through the posts to create the dam structure. And then you can, depending upon the type of BDA and what you want its function to be, if it is meant to create an actual pond upstream, then you would also pack that structure, the branches inside the posts with mud and rocks and dirt and try to seal it up as best that you can. And also maybe provide some tow protection upstream, like a rock layer or small rock layer, or more willow branches, a dense layering of a brush mattress, something like that, to help prevent maybe erosion and scour underneath in that. But the goal is in these incised sort of downcut straightened channels and that where velocities and erosion is pretty significant, that can we come in and sort of put these beaver dam analogs in as speed bumps, right? To sort of slow the flow down, create some flow diversity, redirect flows into the banks and the like, and that in order to maybe start creating some channel widening, or maybe some sinuosity, inducing some sinuosity into the channel, that can, with that channel widening, you can tend to get that reduction in energy, which can then allow sediment to fall out, and sort of accumulate, and then maybe build the channel bed back up in this incised channel to hopefully then maybe reconnect the floodplain, right? To get the water to spill back out into the floodplain. Now, this all takes a lot of time, but this is the goal, is to create widening. Also, as it creates widening and sinuosity, that also creates an influx of sediment into, as it erodes these outer banks, right, to widen and induce meandering. It can create a sediment influx into the stream that if there is another beaver dam analog or the like downstream, that can then trap that sediment to help promote that aggradation for floodplain reconnection. So the hope is over time that it will take it from a straight incised channel, high velocities, through a process of widening and meandering or and the like, and sediment aggradation that then could reconnect the floodplain. And as it does sort of raise that channel bed back up with that sediment aggradation, that the hope is that the groundwater table will also be raised back up and go from sort of draining away from the vegetation in the floodplain to maybe really refeeding the vegetation to give it the water supply it needs to improve the riparian zone as well, right? Or maybe you then also come in and do some riparian vegetation plantings that then that water can then feed to help grow. And the like. So the goal is over time, with the natural processes that are occurring, that you can get maybe channel floodplain reconnection, some ponding and water retention, sediment storage, nutrient storage, right, in a way that is similar to the natural beaver dams that form out there and their complexes. So how do we build them and what do you need, right? BDA materials and equipment include all the stuff that usually goes in beaver dams, natural beaver dams. So essentially wood posts, typically non-treated because you are putting them in the water, and then willow, and we use pine posts and the like, that we tend to sort of point the end of them so that they go easily post-pounded in. And then you need some kind of natural vegetative material such as wine or wine. You can see where my mind's going. No, anyway, willow or pine branches, rocks and mud to sort of seal up in between the posts and that. And ideally, to pound the posts, you need a post pounder of some kind. You could use students with a sledgehammer. They don't really like that very much, so we don't do that very often. But ultimately, usually it is a hydraulic or pneumatic post pounder. And as you can see in the picture here, I do have some students working with my colleagues at the Lands Council and Fish and Wildlife to pound in the posts out at Thompson Creek. And so this is a hydraulic post pounder, similar to fence post pounding, right? And that essentially you just have to have something that can be helpful in pounding in the posts into the ground. Overall material cost and labor, these are very inexpensive structures to build. In particular, if you can source the material that you need, maybe for free. So we have a good connection through our local nonprofit here that is a colleague or collaborator on all this work with me, called the Lands Council, and they actually can go out and source from thinning and cutting on some private property owners. They want to thin out some of the vegetation in the pine vegetation that they have for like fire risk and the like, but they'll go out and they'll allow us to go out and cut and thin a lot of their branches, and then they'll just give them to us for free. So we essentially can source for free the weave material that goes into the BDAs. And then really in these projects, we're only paying for essentially the posts themselves, and then the labor and the equipment, maintenance equipment, right, to actually build them. So they can be pretty inexpensive structures to build. Now it can accumulate a little bit if you're putting a lot of them in, but for the most part, anywhere from $500 to $5,000 a structure, and it really depends upon how big the structure is. We're probably on average around $500 a structure, if that. Some of our projects are even like for 18 different BDA structures, we're only spending about $5,000 total, right? And that on all of that. So they can be very inexpensive, which is why they're also worth trying out, right? So they're not very expensive to build and put into place, right? And it really just comes down to where you can source your materials from, and if you can get creative with that, or if you can use more students to do good free labor. So how you design a beaver dam analog complex and how we've been sort of looking at it as well. There are some good reference manuals out there. There is Joe Wheaton's out of Utah State. They developed the low-tech process-based restoration design manual, LTPBR. And there's a lot of good information in there about all different types of beaver dam analogs, along with other low-tech process-based restoration applications. So that's the low-tech process-based restoration manual. There's also the Beaver Design Guidebook, which is put out by Janine Castro and Michael Pollock and the like. So there are some good references out there for beaver dam analog complex design, sort of guidance documents, not really standards or anything, but more guidance documents along the way. But really, we're looking to build these structures in a river reach as a complex, right? So a single standalone beaver dam analog will not really do its job, and it probably won't last very long. And that, just like a natural beaver dam that's all by itself in the middle of a creek that has high velocities and energy, probably won't last very long either. So we try to build off of what the beaver do with a series of beaver dam analogs in order to help promote their success and stability in the reach, right? So just a bit of background, we've been doing this here in Eastern Washington since 2016, and it's a partnership between myself at Gonzaga University, and I use a lot of my undergraduate students to do a lot of this work. We are undergraduate only, and so it is a great opportunity for our undergraduate civil engineering students to really get their feet wet, right, and dive into a real project that hopefully will help improve the ecosystem and the natural environment. And in the pictures here, you can see there are a lot of my former students that have been working on these projects with me. We collaborate with the Lands Council, who I mentioned before, who's a local nonprofit on land conservation and the like, and then also with U.S. Fish and Wildlife Service. They have an office here in Eastern Washington out of Turnbull Wildlife Refuge, and we get the equipment and some of the funding from them out there at Turnbull. So it's the three of us. We like to call ourselves the Dream Team, and that three organizations is the Dream Team working on these projects in Eastern Washington. Our ultimate goals for all of these projects are really to look at reducing downstream sediment loads. We have a lot of sediment issues in rivers here in particular because of the pollution, and in those watershed areas, and that lots of sediment input from ag. Also, we have some, of course, is prevalent across the country too, some TMDL issues with respect to total phosphorus and toxic algae blooms in some locations. So we're also looking, and Washington Department of Ecology here recommends as a supporting BMP for TMDLs, and in particular total phosphorus, to use potentially beaver dam analogs to create that ponding, sediment, and nutrient retention within the river reach to stop it from going downstream and creating algae bloom problems, right? Also, we're looking to improve habitat and flow diversity, as well as reconnect these straightened and incised channels back to their floodplains. So these are our goals, very broad, very vague, but overall gives you an idea of how and where we're trying to apply these beaver dam analogs to help improve the ecosystem around. Our project started, once again, we did a pilot project in California Creek back in 2016. We had another project that actually went through 2 phases in Rattler Run Creek, which is, so California Creek and Rattler Run Creek, and also the third one, or the bottom here, Spangle Creek, are all in the Hangman Creek watershed, which is that Palouse draining watershed. And then we have an additional project in Thompson Creek, which I'll spend a little more time on Thompson Creek today, that has a TMDL for total phosphorus going into Newman Lake. It is the primary draining creek into a local lake here called Newman Lake, and they have a total phosphorus problem in Newman Lake. And Thompson Creek provides 46% of the total phosphorus going into Newman Lake. And I'll talk a little bit more about that down the line, but we're trying to use some BMPs here to help address that total phosphorus problem. Beaver dam analogs as BMPs, right? So just some quick background on California Creek. This was our first one that we tried to play around with beaver dam analogs in, and we started off back in 2016. The goals here were for sediment trapping, increasing roughness and hydraulic diversity in the stream, reducing erosion on these outside banks that were eroding pretty heavily, maybe try to deflect the flow away from the banks, and that improve habitat conditions. And then this was really an attempt for us to sort of learn about these. We started with really just putting in 4 single BDAs, and over time we added 2 additional, 1, 2, 3, 4, 5. Well, we lost one of them and then came back and tried to add in some additional ones to have them act more in series. We had as you can see from the before BDAs in the left picture here, and then we have some of my students helping to build them. You can see that they have in the after BDA photo here that we've definitely spread out the flow. We've moved the flow around and created more flow diversity. We're pulling some water away from these outside banks, which were eroding into the landowner's property that he didn't really like. And the like. So we've created some habitat improvement here and some flow diversity. In the end, this particular location wasn't very good for creating a true pond that would create sediment, but also too, this channel substrate material in California Creek here is basalt and like big basalt rocks and the like. And it was actually really hard to get the posts pounded in such that they would be stable. So channel substrate material can be really important to BDA stability and making sure that those posts can stay in place and they're in there pretty solid and not like sort of wiggling around and can pop out. And so we were running into some problems with being able to keep the posts stable. And this probably wasn't the best site to put them in, but we had landowner buy-in for it to allow us to do it. And then also we thought, well, let's give it a shot and see what we can learn, because overall they're pretty cheap to install. And then we're using my students in that we could sort of monitor what was happening and that. So in the end, we learned a lot from these, and they did create some good ponding and flow diversity and habitat improvement in that. And we learned some more. Also, the two big takeaways on this is having good substrate material to make sure the post can stay stable and the structure can stay stable. And then also the more BDAs, the better in that. So the more in sequence, the more in series and the like, and the more that you can use, it can help take, if you put more in, it takes the stress off of a single structure, right? So it can reduce the energy related to that. So those were the sort of the big takeaways we learned from that. So then we went to Rattler Run Creek, which was the image before that I showed as well. And that, which is also a straightened and incised channel that really has downcut, lowered the water table. They do agriculture right up to the edge of it, but also you can see there's not much in the way of woody vegetation out here. It's really reed canary grass, which we have in abundance in Eastern Washington, quite invasive and the like, but we have lots of reed canary grass and that, but not a whole lot of woody vegetation. So our goals here were to try to put in these BDAs as speed bumps, slow down the flow, create ponding. In particular, this is out in the Palouse Ag. Can we get sediment to fall out in the ponds created by the Beaver Dam analogs and sort of trap that sediment, retain that sediment in the reach, raise the channel bed back up to hopefully reconnect to the floodplain. And then also, in addition, the Lands Council went out and planted veg out in and woody vegetation out in the floodplains that hopefully that water can then feed and get to grow again. And that. So those were sort of our goals for this. We ended up doing this in phase 1 in 2018, and then we came back and added a bunch more in 2022 and that. And so the after BDAs here, you can see we put in different types. I'll talk about these different types of BDAs in just a second with Thompson Creek and that, but we put in some constrictor dams, some secondary and starter dams, or primary and secondary dams, and channel spanning dams, and that, all attempting to create the ponding and the slowing of the flow, and then hopefully the flow to get the flow to kick back out into the floodplain again and raise that groundwater table up. And we have noticed and in this particular creek, the channel substrate was really good for pounding the posts. It was more of a, not quite a clay material, but more of a softer material that actually allowed the posts to go in and stay pretty stable and that. And so we have done a good job on this one so far of creating ponding and attempting to raise the groundwater table back up, but it also takes time, right, to work through that. The most recent one that we just put in last year is Spangle Creek, another creek similar to Rattler Run out in the Palouse, and that a straightened ditched channel. And in this particular channel, it tends to run dry for a lot of the year. And our goal here was hopefully to retain water longer. So to keep the water in the creek. Also, the Lands Council had planted veg, as you can see in the building BDA's photo here. You see some of these alder trees here that they were actually planted, and we wanted to keep the water longer and closer up to the floodplain to feed that vegetation that was planted. So we came in and put in I think there's like 7 BDAs in this stretch, 7 to 10 Beaver Dam analogs in this stretch in order to do what you see here on the right. And that, so create the ponding to feed that vegetation. And then the hope is that hopefully it'll stick around longer. The water will stay in the creek longer to sort of retain it and slow down the residence time as it moves downstream. We don't think that it'll keep water in there permanently all year round, but the hope is at least to give it some longer time of retaining the water in the creek. And that in this stretch to feed that vegetation to keep that growing. And that. Okay, so the big one we've been doing, and the one that I've been diving the most deeply in with monitoring the effectiveness, is Thompson Creek. And this is, once again, just outside of Spokane, Washington. It's almost near the Idaho border in that, but just northeast of Spokane. And you can see in the image here, there's Newman Lake, which is up here in the upper left of the photo. And Newman Lake has a TMDL for total phosphorus. And Thompson Creek has what is the only actual surface water source into the lake. And it actually was straightened and essentially ditched and straightened in order to use the floodplains for pasture as well as some ag a while ago. That no longer is being used. So this whole downstream reach going into Newman Lake of Thompson Creek is no longer being used for ag or for pasture. And so the landowner has been more than willing to allow us to go in and try to reclaim that. With respect to using the Beaver Dam analogs, creating the wetland environment and the floodplain, reconnection to the floodplain that we might need to help maybe reduce the phosphorus loads running into Newman Lake. So hopefully retaining both sediment and phosphorus in the creek itself to then be uptaken by the plants and used in there, rather than allow it just to sort of straight shot into Newman Lake, which is what it's doing right now. And that, so our goals are, and in particular, too, Washington Department of Ecology sort of recommends Beaver Dam analogs as supporting BMPs for nutrient TMDLs and the like, too. So we were sort of following on with that and trying to see how well they could work here to help reduce the total phosphorus and help that TMDL. So our goal, too, is reduce velocities and promote ponding, increasing roughness and hydraulic diversity, floodplain reconnection, right? And then also maybe improve the habitat characteristics for the macros and the fish, right? So we first phase, and actually what's in there now, is we designed 18 Beaver Dam analogs of different types, which I'll show you in a second, to go through this to be added to this roughly 1,500 foot long reach. And we're still looking in the same direction, but you can see where we put in the yellow lines indicate several of these 18 BDAs that we have installed, and some of them, in particular, the downstream ones, are doing a really good job of creating ponding and floodplain reconnection. But there's always a lot to learn along the way too, and watch as the natural processes. So now these are meant to be sort of process-based restoration. We put them in and let the river do the work, right? Based on the natural flow regime, based on the sediment loads that are coming in and the like. And so it usually takes minimal upfront work, but then it can take a lot more time. You have to be patient, right? And watch Mother Nature sort of do its job, and then sort of learn from that and potentially adaptively manage the Beaver Dam analogs that are in there. I am not a big proponent at all of installing these and walking away from them, right? And so ideally you should be sort of watching and reviewing, and then maybe if it needs some adaptive management to try to help keep those processes moving in the right direction. So we installed 18 of those 18 BDAs. We had 4 different types that we designed as sort of series of complexes. And so this also is from the low-tech process-based restoration design manual. They give a lot of information on these different types of BDAs and their function. And so you can see in the lower right table here, there are primary dams, secondary dams, channel spanning dams, which are considered not ponding. They're really just meant to add roughness. And constrictor dams or constriction dams, which are almost like deflector dams. They're forcing water to move in the direction you want it to create erosion in key spots, right? So the primary dams are really meant to simulate the dams that beavers build to create the pond that they have their lodge in, right? And then usually they have at least 1 or 2 sort of quote unquote secondary dams downstream of their primary dam to help protect their primary dam from maybe head cuts moving upstream, or also to backwater and create more roughness and ponding and lower velocity so that their primary dam doesn't get blown out. So we have complexes of 1 primary dam, or sometimes we call them starter dams, and then secondary dams as well that go along with them. And then we've added in strategic spots channel spanning dams, which are, so first off, just step back. The primary and secondary dams are meant to be sealed so that they actually create ponds right upstream of them. The channel spanning dam is essentially weaved but not sealed. It's meant really just to provide roughness, right? And slow the flow down between maybe the starter dam complexes and the like, right? So it just adds in key locations where maybe velocities are high and the like, that you can add in these channel spanning to help sort of increase the roughness and maybe create some flow diversity and widening and the like in those areas. And then constrictor dams, as you can see in the drawn image here, they are actually meant to force flow. And in the image here, you can see force flow into the outer bank so that it creates erosion and sediment inputs, which then that sediment comes into the channel, gets carried downstream, and then hopefully retained behind the next downstream starter dam. So we would put constrictor dams upstream of starter dams so that when it creates the erosion to increase the channel widening, as well as to maybe promote sinuosity, that sediment can get trapped and behind the next downstream starter dam to help also grade the channel bed back up to reconnect to the floodplain. So they're sort of strategically placed in locations as well. So to actually come up with our overall complex design here, I used what's known as a relative elevation model, which looks at high points and low points from LiDAR data of the river and the floodplain, and was trying to also look at where maybe some old relic side channels might have been and the like, that you can't really see on the ground when it's all covered in vegetation, but the LiDAR data can show you that, and you can highlight it by color coding it based on elevation using what's known as a relative elevation model, which they also use those in stage 0 restoration design for full channel floodplain reconnection and that. But anyway, it helped highlight areas of potentially, there used to be an old side channel here. And so we would put a constrictor dam in a location that maybe would kick that flow out into that relic side channel in that. So trying to use that kind of information to help sort of locate where some of these different structure types should go in that. But you can see that the different structure types have different objectives and functions, and really based on your overall goals and objectives for the project, you would choose these different ones and also put them in series and change a variety of the complex along the way, right? So 18 of them, we have 3 starter dams with secondary dams with it. So 3 complexes of a starter dam and 2 secondary dams, a variety of the channel spanning dams mixed in between. And then we had 3 constrictor dams that were put into this reach as well. And once again, our ultimate goal on this reach was to create some ponding to get the sediment aggradation and also the nutrients or the total phosphorus, also to be more retained within the reach and that. So to create more of a wetland ponded environment rather than the current high-speed highway that it is in that. So these are some results so far that we've gotten. Now, we built them in November 2021 in that. So we put them in the ground in November 2021. I will say that it was super cold and the water was very cold at the time, and it was really hard to seal the starter dams, to get in there physically, because it is usually physical labor, right? You are in there and trying to pack them and seal them with mud. The water was really bitterly cold, and so we found it very challenging to get the starter dam sealed at that time. And the hope was that we would come back the next summer, but we get our big spring freshet that happens from the snowmelt runoff and the like. And so we had a lot of erosion that happened right off the bat because we didn't get the sealing that we wanted. We also have an issue out here of, well, it's not really an issue, but it happens. The middle picture there, you can see the ice layer. We get ice that forms over essentially puts a lid on the creek in the winter, and the water is still going under and flowing under that ice lid. But when it runs into the BDA structure, if it has that ice lid on top, it can't go over the structure. So it's looking for another way to get around, and it's been tending to scour underneath. So under the weave material and that. Now the posts are pounded. You should pound the posts at least half the length of the post that you're using. And then different elevations, you build the BDAs to different elevation depending upon your objective and the like. But ultimately, we were getting the water to scour under the weave material, and essentially the water was just going under. So it wasn't allowing for ponding to happen, and essentially because it was eroding the channel weave material underneath. Also, as you can see in this picture, this is a starter dam from November 2021 when we built it through this past January in 2024. I just went out and took these 3 images. Essentially, they're 2 years apart. And you can see that the channel is starting to cut around the starter dams. It also has been going under the starter dams, as I mentioned before. But this isn't a bad thing. This does not mean that they are failing and the like. They aren't necessarily creating the ponding that we originally intended, but they are creating this sort of first phase of what these beaver dam analogs should be doing, right? So they are widening they're attempting to widen they're allowing for channel widening, as well as increasing sinuosity, and that which can also then eventually lead to sediment deposition, right? Because you're releasing that energy by widening the channel. So we're getting some initial, and it's only been 2 years as well, and that. So we're getting some initial reaction to the Beaver Dam analogs in a trajectory that seems positive, right? With at least decreasing stream energy and hopefully eventually creating some more sediment deposition along with phosphorus. And the like. And so this is the second starter dam that's downstream of that last one. And you can see we're getting an increase in this case, the flow is still going under these, but it also is increasing wetted area upstream as well after 2 years. And then this is the third starter dam downstream where we're seeing a little bit as well in increase in wetted surface area and a little bit of ponding happening upstream, right? This is data that we actually measured for surface water area upstream of the 3 starter dams over time for just the 2 years that they've been in the ground. And we are seeing, as you can see in this image, this is pond surface area measured upstream of each of the starter dams, and we're getting an increase in pond surface area. So they are creating some ponding, but not enough yet to really trap sediment and phosphorus behind it, and in particular because of that erosion underneath. But you can see the sort of ponding that's happening here in the picture. This is starter dam number 2. We've also gone out and done repeat cross sections. So we have 3 standard cross sections located about 10 feet, 20 feet, and 30 feet upstream of each starter dam with rebar that are permanent out there, so we can go out and repeat survey and that the channel bed elevation and the floodplain elevation, right? The entire channel cross section repeatedly at the same location over time. And this is starter dam number 1, which has the flow cutting around it. You can see from the 2 years of it being in the ground and that the repeat cross sections of the channel bed, you can see the channel cut around is shown up here in the orange. So June of 2023, you can see the channel is starting to cut around. We've gotten some aggradation happening upstream in the area of this starter dam that doesn't have the cut around, right? It is creating some ponding and slow flows here, which we're getting some sediment deposition. It eroded, and now it's starting to refill again. And that if we move 10 feet further up, and then we're still getting some sediment aggradation happening there upstream of that starter dam in the channel bed here. And then upstream, 30 feet upstream of this, the channel hasn't changed very much. So the influence of this starter dam really is extending about 20 feet upstream or so. But also because the flow has kicked around it and that it isn't really acting as a true beaver dam that's creating a big pond, right? And the like. This is starter dam number 2, similarly with repeat cross sections. Now, this particular, and you can sort of see it, that the posts are starting to lean in the middle in the downstream direction. So flows going left to right in these pictures. And that this one in particular was getting that scour under the ice phenomena. And you can see it's sort of starting to undermine this beaver dam a little bit, the posts with their embedment and that. So what we attempted to do was to try to seal up that hole. We ended up excavating. So this change in channel cross section for the orange, we went out and sort of dug out some of the channel bank here with the reed canary grass clumps to act as fill material to try to seal up that, or fill in the scour hole that happened underneath and maybe attempt to seal up some of the dam. So some of this was adaptive management. These changes in cross section that you see was our own adaptive management to try to create more stability for the structure, but also to maybe seal it up again too. And that. So overall, we haven't had a whole lot of change upstream of starter dam number 2 because a lot of the flow has been going underneath it. And that. And then the last starter dam of the complex downstream, we're getting a little bit of aggradation in the middle happening. It is creating some floodplain reconnection down in this lower end of the reach. As well, we see the water during the spring flows spilling out much more readily out into the floodplain in this downstream location rather than the upstream ones, but still, so it's creating some floodplain connection down there in that, but not a huge amount of change yet that we're seeing. With respect to the total phosphorus and the TMDL, we have set up a quality assurance project plan with the Department of Ecology to test total phosphorus. We're sampling water samples that get tested for total phosphorus upstream of the reach, halfway down there in the mid reach, just downstream of the second starter dam, and then at the downstream end of the reach, sampling water monthly and that can then get tested by a local certified lab, and that for total phosphorus. And what you see in these images here are the upstream, mid-reach, and downstream sample every month. And then these are sort of the box plots of changes in total phosphorus concentrations over time, at both after the Beaver Dam analogs have been put into place. And the idea is that we're hoping to see essentially the upstream sample have higher total phosphorus than the midstream and the downstream one, right? So we want to see a reduction in total phosphorus in the downstream direction. Currently, as you can tell by these box plots, we're not seeing that dramatically a difference in that. So in the end, right now, it's only been 2 years though, and the channel is still adjusting to the Beaver Dam analogs that are in there. They aren't quite creating the ponding that we originally intended, and we're trying to work with that. And we're also thinking about maybe adding some additional Beaver Dam analogs and trying to seal them more properly than we did, because we didn't get a chance to do that in the first round. So anyway, we're looking at this further, but once again, it's only been 2 years. Process-based restoration takes time, and you have to be patient in that and sort of watch what's happening. Macroinvertebrates are showing a good positive response to our Beaver Dam analogs. We're increasing diversity. There is an increase in diversity of macroinvertebrates within the locations of the BDAs compared to upstream samples where there aren't any. So we're showing a good trajectory in habitat improvement as well as macroinvertebrate diversity that's happening within the BDA reach. All right, so overall, lessons being learned for sediment nutrient trapping. There is huge potential for this because they're cheap, and that they're fairly easy. They're a little bit, they can be a little laborious with pounding in all those posts, but for the most part, they're fairly easy to install. They're very inexpensive to install, and the like. And so there shows pretty good potential with them being used. That we are showing in some cases some good aggradation and sediment trapping if the BDAs are creating the ponding that we want them. Their original intended function was to do. But in addition, they can also just create channel widening and the like, which also can create sediment inputs for aggradation downstream. Right. And so a BDA that doesn't pond is not a failure, right? Ultimately, they still function, even if they start to degrade, if flow cuts around them, they still are providing good function for improving hydraulic diversity and habitat and other good ecosystem functions, right? And that over time. So once again, they're showing good habitat improvement and increasing macroinvertebrate diversity. They do require adaptive management, and also to keep watching them to learn too. These are all relatively new structures that are being implemented as low-tech process-based restoration. So even just monitoring and adaptively managing them can get good information out there on how to improve their use and function, right? So we do know that BDAs in series are much more effective than individual. Channel substrate material is super important to getting post stability. And also maybe limiting the amount of scour under, depends upon how erodible that channel substrate material is. BDAs must be sealed, ideally to get the ponding. And then inexpensive overall, they're inexpensive to build, modify, and they're fairly low risk. Now you do have to think about if there is infrastructure around, and that, like if you're putting these in upstream of, say, of a culvert, and they do fail, you're inputting that wood into the system, which can go downstream and clog that culvert, right? So there still is some risk involved that you want to think about as you're thinking about designing these and the like. So so we think about those kind of things as well, right? So overall takeaways: beaver are indiscriminating rodent that is really good as being an ecosystem engineer. Their dams provide important ecosystem services, increase stream resilience. They can maybe be used to buffer the impacts of climate change and wildfires, right? Beaver conservation and restoration and the use of BDAs are cheap and cheerful and low risk, so why not try them? Expectation management is critical, though. Beaver restoration won't work everywhere, and in particular, be patient, right? Process-based restoration can take time, and so you just have to sort of give the channel the opportunity to help restore itself, right? So remove the impacts, give it some chance to start, and then let it sort of take over. And so with that, there's Beaver Dam analogs in Eastern Washington.
Well, thank you very much, Sue. Hey, I have a question with you related to kind of phosphorus reduction, are there any things that you're thinking about from a process-based design that you're concerned about? Hey, this may be a way that we may not get the reduction that we think we would out of beaver dam analogs that hasn't been accounted for, or kind of what are your concerns related to nutrient reduction? The idea of, hey, sorbed phosphorus will deposit behind these structures seemed to make a lot of sense. Is there anything else that you guys are trying to think about right now?
Yeah, I mean, for the most part, that's what our goal is we're trying to get that phosphorus to be retained in the ponds upstream that hopefully then can be used by the vegetation, right? Rather than having it just be transported downstream. And also, even if the dam sort of fails and releases that phosphorus, that the goal is that even if the rest downstream, right? If the river environment is such that it isn't a high-speed highway, right? That nutrient can maybe deposit downstream and be used by the vegetation there. But that process is important, and right now, right, we're learning, but once again, we've only had them in the ground for 2 years. So, but is that ponding process is really what's important. It's creating the pond to create the sediment to fall out, right? And that to retain that sediment with the phosphorus, because the beaver dam analogs themselves do not filter phosphorus out, right? And that the water, they are somewhat impermeable no matter what, and so they don't act as a filter, but it's about creating the pond, right? That depositional environment that then reduces the phosphorus. And at the moment, we're not getting that ponding that we really want because of the scour underneath the weave material and the like. So, but the hope is that over time, if these continue to widen the channel, that will create deposition, right? And that with the phosphorus as well. So we're sort of learning as we're going here too, but the goal is to try to hopefully retain that phosphorus in the reach rather than let it go down into Newman Lake where it's causing the toxic algae bloom problems. Did that help?
Yeah, that helps. Yeah. Final question I have a bunch more, but I probably won't list them now. I might ask you later. But we're seeing a lot of people get excited about beaver dam analogs, but we're also seeing them starting to get applied in places where there's just not wood nearby. Has there been a thought in the community of how to get the same effects for beaver dam analogs, or what to call these things, or is it okay to do a beaver dam analog when we're not using wood material, when we're using something other like hay bales, if hay bales are available, or, so has there been any thought of what it looks like when wood just isn't available?
To build them, you mean? Yeah. And not necessarily wood for beaver to take over. Is that what you mean? Yeah. So, yeah, I mean, if they can simulate the process of beaver dam, they can be, because you can even build them out of postless structures where it is just like a bunch of wood piled up and the like. There's also post-assisted log structures, but it is possible, I think, to build them out of hay bales and the like, but I would wonder about their stability and degradation over time. It just depends upon what your goal is, I suppose, and how long you wish them to sort of remain in the stream doing what they need to do. And that the material over time, right? And then also the process that happens around it, and the like. So I think they can be built now going in. Well, I will say by using wood and natural materials, and that in here, our permitting process is way less, right? Like, because you're putting natural materials into the stream and the like, and they're pretty low impact. So the permitting for these beaver dam analog structures has been pretty minimal in that, because it's a restoration with natural material. If you start building these things out of rock and metal or anything else, I imagine you have a whole lot of permitting issues that you have to deal with.
Yeah, a lot of what our thoughts are is building beaver dam analog type structures out of hay in the Great Plains. So places where we don't have the wood using kind of the grasses as the natural thing. And
I would say with that though, I mean, they're gonna probably erode faster over time, right? So and not be as stable in long term. But that may not be a bad thing, because even if they are eroding, it's just natural hay material that's going into the stream. So, and the like. So I think it just depends upon your objectives and your time frame and the like as to what you're doing. I would lean more on that, the natural side than non-natural side to build these. Yeah.
Well, I really appreciate your time.
Sure.
And I imagine we'll probably have some questions, because we'll stop the recording now and stuff when we edit it. But I imagine we'll probably have some questions for people to come back. And the amount of time that you kind of went over, usually we have about a half an hour. So we may break it up into 2 different sections and give people an opportunity to kind of ask you some questions. We can send you the questions, or we can share your email address. I don't know if you have a preference, either one.
You can share my email address. That's fine.
Sounds good. Sounds good. Yeah, I always want to be careful. Some people get concerned these days.
Yeah, no, that's fine.
All right.
If
Hey, thank
anything
you
looks
very much,
bad, I'll
Sue.
just
I
delete.
appreciate it.
Awesome. Thanks, David.
Have a great day.
You too.